All right, folks. So today we're going to talk a little bit about this UV-5R. So this is a request video, and somebody asked me to take a look at the output of a UV-5R. So that's what we're going to do today. This is an older radio, and I've had it for about 3 or 4 years. I bought it from a reputable dealer in the United States, and it was branded as a legitimate Baofeng. Now, one of the things about these Baofengs are there are a lot of copies, fakes, and clones. And I think that's the same thing, no matter which word you use, that aren't made by the official Baofeng factory. And there's probably some clones and fakes made in the official Baofeng factory. But anyhow, we have this this Baofeng. And when I got it, I believe this to be what they would call new old stock. So they had older Baofengs that they were selling. The reason I think that is the box that they come in has gone through a number of evolutions and design changes. And this had the older original box that they came in. That said, we're going to go ahead, we're going to flip this baby on. And we are working with a frequency of 14652. And the reason I do that is because that is the calling frequency. Now, somebody might come in here and be like, no, son, the calling frequency is 146500. But we're going to do 146520. Now, before we get too excited here, one of the things I wanted to do is take a quick look at a calculator and talk a little bit about why we look at these types of things. So we have 146520. That's what's called the fundamental frequency that we're going to be transmitting on. Some people refer to the fundamental frequency as the first harmonic, and then additional harmonics get numbered correctly or incorrectly depending upon how you do that. We're just going to call them harmonics. So when we take a look at 146520, and let's just say I multiply that by 3, so let me open up my calculator, times 3, we get a frequency here of 139.56. So what I want to do, since this one's already on, let me go ahead and turn on another radio. Okay, so now we have this on that harmonic frequency, and harmonics are actually multiples of your fundamental frequency. So the reason I want to show why this is a little bit of an issue is that when I key this radio up, without an antenna, you can see I'm receiving a signal there. And so if I was going to talk on this radio, that means that I am putting out copies of my signal, albeit they're weaker than the fundamental, but I'm putting it out on other frequencies. And some of these frequencies may or may not be inside the ham bands. They may be on public service channels, and they may cause interference. So it's one thing to interfere with a ham, which is not cool, but it's a whole nother level of uncoolness if you interfere with public service, for example. So just wanted to do that quick demo. Let's go ahead and connect this up to an oscilloscope and take a look and see what we see when we transmit. Okay, we're connected to the oscilloscope via this coaxial cable. And now what I'm going to do is I'm just going to turn this screen on, and now you can see the oscilloscope in the background. And when I key this up, we're going to take a look at the carrier signal. So that's a mess. So let me go ahead and tune that in for you real quick. Okay, so now we're tuned in. When I key this up, remember it was on 14650, so that's the first thing. You can see that my frequency counter on the oscilloscope is actually seeing an output signal at 163.2, give or take, 0.1 something. It's bouncing around a little bit. But what we should see is a pure sine wave there. And the way that the radio works is that it modulates information, in this case our voice, on top of that carrier signal. So you want as clean of a carrier signal as possible. When you see something like this, it tells you it's not clean. So let me just go ahead and stop this. And you can see that our carrier signal is not a sine wave. It's a mess of a bunch of different things. And that's why we get, and this is caused by interference and distortion inside the radio. And that's why we get that frequency counter telling us it's not the frequency that we're transmitting on. And what I want to do, and let me go ahead and turn the scope off, or somebody will claim that I'm cheating. Let me just take this off real quick. Okay, so now we are on a different radio. This is the BTECH DMR-6X2, another Chinese-made radio, but fantastic radio. I love it. Let me turn the scope on, and let me turn off my pause. And then when I go ahead and key up, and let's slow it down. And what you can see there is a nice clean signal, right? It's a nice clean sine wave. And that's exactly what you want to see. So I wanted to show you the differences there. What we're going to do now is we're going to connect these up to a spectrum analyzer, and we're going to take a look at the output from a frequency standpoint, not a voltage standpoint. Okay, so what we've done is we've connected the Baofeng up to our spectrum analyzer. In this case, it's a Siglent spectrum analyzer. And I ran a quick test where I keyed up the radio, and then we have our harmonic results here on the screen. So I want to talk about the screen and what we see a little bit there. We have three markers, marker number 1, 2, and 3. Marker 1 is at our fundamental or our transmitted frequency. Marker number 2 is a delta marker from marker number 1, and that tells you the delta between marker number 1 and marker number 2, or our fundamental and the first harmonic. And then marker 3 is at the second harmonic. When we take a look at the data table, what we see is marker number 1 is around 31.4 dBm, and that is exactly what we would expect to see of this radio on its fundamental frequency. Marker number 2, we take a look at that, and you can see in the table that it's negative 43.36 dB down from the fundamental. You'll see a lot of people do this test and say, oh, it's 40 dB down, it's good, it's clean, you're good to go. Well, in actuality, it has another part of the rule, and it needs to be below negative 16.02 dBm, which is 25 microwatts, if I remember correctly. So anyhow, when we take a look at that blue line that goes across the screen, that is at that negative 16.02 dBm mark. And because our marker is above that, marker number 2 causes the Baofeng to fail and make it illegal. One of the things I'll say is this is actually one of the cleaner Baofeng UV-5Rs that I've seen. It's very close, but legal and illegal is a binary equation. It's not close, so it would be illegal to use. We take a look at marker number 3. Marker number 3 is just above that, but it's down 48.11, which is really good harmonic suppression, but it's not clean enough to be considered legal. So what I've done is I'm in the process of setting up the BTECH DMR-6X2 to the spectrum analyzer. So let me do that real quick, and we'll take a look and see how that one does. Okay, we are plugged in, we're wired up, and we're fired up. Let me go ahead and turn the spectrum analyzer back on, and I'm going to go ahead and I'm going to key up. And so when we key up there, you can see that there are no harmonics coming out of this. So that would be what we would consider a nice clean signal on the BTECH DMR-6X2, and we're very happy with that. Now, the purpose of this video isn't to do a full-on in-depth analysis of the Baofeng. It's just to show you what we look for when we do these types of tests. Obviously, I didn't test it on high and low, but we tested it enough to see that there's problems with the purity of the carrier signal, and then we also tested it to see that it does have spurious emissions, rendering it illegal to use on the amateur radio bands. Anyhow, that's going to be it. If you have any questions, comments, suggestions, or recommendations, go ahead and post them below, and I'll do my best to respond. Thanks for watching, everybody. It's much appreciated.